So I wanted to give you guys a foundation on building AI agents, basically how they work, what the terms are, um, because at some point we're going to be having some guests on that um, are like startup founders of some of these platforms, like Relevance, where you can build these AI agents, um, and they all kind of work the same way. It's kind of a like a wizard that walks you through the various steps of building an agent, defining the tools, setting up the knowledge base and all that. So I basically just wanted to go through that with you guys so that and kind of explain how knowledge base vector storage retrieval works and just some of the basics, and then I'll go into the details of like how the storage and retrieval works with vector databases.
Is it a true agent, like runs autonomously type agent?
Yeah, well, there's two kinds. You can have one with the human in the loop, where it goes through its processes, generates some output, and then asks you if that's correct, asks for your feedback, and then there would be a feedback loop, right, that would
Hmm.
tell it that whether or not it's doing well or not. So an agent is software that perceives its environment, makes decisions. That's the key point, and takes actions toward a goal. And it typically uses a task-based framework. So you can have a director agent that figures out what the steps are and directs other agents, or you can have one agent that does everything. Typically, you want an agent to be specialized in a specific task.
Right.
Um, so you can build teams of agents that each have specialization. If you think of like a business department where everybody's specialized in their own jobs, then you have a manager and a supervisor and a CEO, right, that manages all these. And a lot of people refer to those as agent swarms, where you just basically have a team of agents, everybody's doing their own thing, and then they all come back together and report to the supervisor, the manager, or the CEO, or whatever. So you can think of them as digital coworkers that learn over time. They take feedback, and then they learn from their mistakes or their successes based on that feedback.
Right. Cool.
And then obviously what you can do with agents is you can answer questions like with ChatGPT. That's not really an agent because it typically doesn't have access to tools, but that's the key difference is that an agent can make decisions and it has access to tools. And typically um, you can create a tool, and once you tell the agent it has access to that tool, you don't actually have to tell it to access that tool when it needs it. It'll figure that out
But that's the
once it has that.
autonomous part. That's the autonomous part.
Right. So once it defines what the tasks are that it needs to perform, it's going to know what tools it needs to use based on the definition of those tools. And then, ChatGPT has memory. You want to manage state in agents with memory so that they can keep track of like where they last left off of a task, or they know who they're dealing with. So you want to manage state with memory.
Yeah, I was just going to say that isn't that state machine dependent? It has to be
Right.
able to manage that. If it doesn't have that capability, then it wouldn't be able to do that.
Right. Especially when
Yeah.
you're handing off from one
Right.
agent to another. You want to have a shared state so that
Yeah.
you can track what everybody's doing.
Or you could have a listener or something that checks the state, because the biggest downfall in a lot of organizations is they just go forward assuming after a given period of time the task will be complete. But if it's not, it causes havoc. So it's always, if you're building these kinds of things, it's always good to either have a shared state, as Chris said, or if you don't have a shared state or can't get a shared state, to check on the state of the task upon which you are dependent. That's one of the biggest things throughout the history of the world on these kinds of things that causes things to go awry and blow up. So just if you're building these, make sure you take that into consideration, because if you don't, it can cause a really big amount of problems.
Right. And then a lot of people ask, what's the difference between an agent and an automation? An automation follows a predefined set of instructions, just like a computer program would, whereas an agent can adapt to various circumstances and it controls its own logic. So that's the difference. An automation can be a tool, and typically that's how you create a lot of your tools. A lot of your tools are going to be these static workflows that an agent's going to have access to that it can actually trigger. And then I was just talking about teams and how those are structured. You want different agents to have specialized tasks so that you don't have one agent that's doing everything. You tend to it tends to make mistakes if it's overwhelmed, and you can't cover all that in your prompting typically. So you want to have agents with specific tasks. You want to have collaboration. And then we talked about that with the state machine, handing off tasks, tracking tasks. And typically that would either be in memory or a database to track. And then you can scale with new agents, and you can even have agents create new agents. So you could have, say, if an agent had realized that it needed to accomplish a task and it didn't have an agent for that, it could spool up an agent and then spawn that agent to go complete that task.
Chris,
that's not typical.
Hey, Chris, sorry to interrupt, but would you be able to provide like a use case for this? Where would these be used and in what capacity?
So anything that a human can do on a computer, you could employ an agent to do. So a good example would be, say I'll just use a simple use case, like you're running a blog website and you need, or you're creating, you have a publication, a research publication, and you need researchers to go out and perform research for the various sections of that publication. You could spawn these agents to go out and do all the research for you. So they could scrape the web, they could pull in relevant research articles, compile all those together. You could have them go out and do this on a daily basis, and then you could have one agent that collates all those articles and makes the decision on which ones get priority. And then for publishing, you could have a separate agent that actually goes out to the website and publishes your articles. So that would be a simple example.
Okay, thank you.
Mm-hmm. And here's another example, HR. Like everybody wants to replace HR, right? So you could have one, and this is a great use case for the voice AI stuff where you have, you want to conduct interviews and pre-screen people to find out whether or not you want a human to actually spend time with them. You could have a screening agent that does that, a scheduling agent that schedules on the calendar, onboarding agent that handles all the paperwork and answers all the routine questions, sends new info, and HR policy Q&A. Most people have intranet site that has all the Q&A stuff, but you could create, say, a voice agent that answers all the questions internally. You just dial an extension and they could get that information in any language over the phone if they needed to. So that would be a good example there as well. The structure of an agent is you have a user interface, which would be, say, a chat interface or a voice interface right now. And then, in the future, they're talking about having AI augmented humans where you have a direct to brain interface. That's obviously down the road, where you just think something and the agent responds to what you're thinking.
Oh my God. It's bad enough 11 Labs has AI agents that'll make phone calls and have conversations with people.
And then the LLM, the large language model, obviously you want to pick the right one for the task that you're trying to perform. A good example of that would be, say, GPT-4o, versus GPT o1. So o1 does all the chain of thought prompting for you, and it can actually do some reasoning tasks, whereas o1 just gives you information. You basically would have to give it the framework you want it to follow, whereas o1 could actually like come up with that itself. And then there are other lighter frameworks. Say if you have an internal data store and you don't want it affected by the base, all the knowledge that it's been trained on that on the internet, you could get a lighter model and just have that interact with your data store so that you're not polluting it with all the outside knowledge, basically. So you want to make sure you put the right model and for your large language model. And by large language model, I mean ChatGPT, Llama, and the Claude, Anthropic. So you want to make sure you pick the right one. Claude is better at writing. So if you're doing some creative writing, you probably want to pick Claude versus GPT 4o. Although I think they're kind of even on creative writing. Maybe not, but most people prefer Claude for that. And then memory, we just talked about that. Keeping track of context, conversation history, and past user inputs. And then information, obviously this would be information about the user, any interaction with the user. And then you want to have a knowledge base for all your documents and any past interactions. So if you have policies and procedures in the HR example, you'd want to store all those in your knowledge base. And as you're interacting with the LLM via chat or voice or your brain, it would pull relevant pieces of information from that knowledge base. And vector stores are the way that that's done right now. And I'll explain that here in a minute. But basically, you're talking to the LLM, you're giving it a query, it goes to the knowledge base, pulls out relevant pieces of information from that knowledge base, and injects that into the prompt for the final answer, so that it has more context in relation to your query. And then for tools, you want to have a tool can be an external API. So if there's say a government database out there that has government contract information, and you want to have an agent go pull information from that government database, you could have a tool that does an API connection to that database. Anything that has an API can be a tool. Or you can also have internal tools that do various functions. Inventory is a good example. So you have a tool that's connected to your inventory system. I could ask the agent to go out and tell me what I need to reorder from my inventory, and it would go out and check that inventory database and come back and tell me what I need to reorder. And then we talked about the human in the loop, basically through any one of those tasks. As it's going through any one of those tasks and it needs approval or it needs feedback, it would stop, send a human a message, or ask the user, is this right? Is this what you need? Is this correct? And the user could provide feedback or give it a better example of what the user is looking for. And then, of course, capture human feedback, which is what I just mentioned. I'll go through this and then I'll come back to the knowledge base thing. Well, I just covered this. So you want a single specialized agent that's very good at doing one thing, and then you want to assemble a team of these. And typically you would have one director agent that would decide which agent it's going to delegate to, and then have that agent report back to the delegator agent. So we talked about how AI agents are goal-oriented and they adapt to their environment. Multiple agents can collaborate for larger workflows. And then for this, you'd want to identify kind of the lowest hanging fruit in your organization where you could start to augment humans with agents. Basically, give them helpers. Like I always say, you don't want to replace them; you want to enhance them. So any tedious tasks, research is a good example. If somebody's spending a lot of time going out and looking things up for their research, you could have an agent do that. I know an example where somebody spends like 10 hours a day doing medical encoding, and I'm not really familiar with that process, but it's a tedious process. And I think an agent would be a good candidate for that as well.
Mm-hmm.
So you just basically spawn this thing off, let it go do its thing, report back to you while you're doing more important things. And
that's a really good example. I really like that one because the healthcare industry has literally tens of thousands of people doing coding and are doing most of it. Most of them are credentialed medical professionals.
Are they matching like CPT codes to diagnose this?
Yes.
So that's what you're talking about. Yeah, you can easily.
So they are, and they're mostly nurses. The only problem is I don't know the regulatory requirements of that. I don't know if it has to be done by a credentialed medical professional because usually it's a nurse, usually an RN or an LPN.
I don't think it does unless it's changed, but
I think if you had an LPN or an RN approve the algorithm that does the coding, the regulators would have a hard time disagreeing with it. That might be huge for some. You probably have to have a documented process that says that, but yes, coding is a drag.
As long as it's supervised by a human, they probably wouldn't have a problem with it. And then the time that you save with this, you want to spend on, FaceTime with your customer or improving customer experience or whatever. But typically you can take that time that you save using these to improve your customer service. And then let me go back to this knowledge base.
But they're the medical community. They don't want to improve customer service.
Well, maybe not in that particular example.
No, but that's a great example. And you probably have to have a nurse or a licensed coding agent approve the workflow, right? And double check it for a while. But after a given period of time, that could save millions a day in healthcare in the US.
Right.
And as long as you gave it feedback on how it was doing, it would improve over time.
Well, Sherry brought up a good point in the chat. Think about it from the healthcare side. Here they are validating and checking and accepting or rejecting these claims that are coming through with specific CPT codes and CPT 9s to authorize them. Imagine how many they can eliminate and how much time, energy, and money they could save.
Well, you have to be very careful about that. I agree, Steve, but I think you have to be careful about that because one of the big healthcare companies is facing a multi-million-dollar lawsuit for rejecting claims doing exactly that. And they weren't properly comparing them to the ICD-9 and 10 codes, and they were rejecting them based on cost. And so they're facing like it's $50 million. So I agree with you, but I think you have to have some kind of documented procedure that would back you up on that, which is cool. I think to Chris's point, you'd still could save a lot of money there and only have the actuaries and underwriters look at the things that are acceptance that don't fit the mold. And I give you, it's a Chinese menu, but it is finite.
So I'm going to go over the components of an agent and basically how they interact. So as I mentioned before, you have a chat interface, chat voice. A lot of people are using SMS now so they're using that for marketing where they're automating a lot of their SMS messaging, and even having conversations with people over SMS. So you get user input through the chat interface, for example. The user provides instructions, and the large language model provides a response. And then you have the memory for state. So the large language model is saving information about the input to memory. It's retrieving information from a knowledge base, which is typically a vector database. We call this, people refer to it as RAG, Retrieval Augmented Generation is what that stands for. And then it has access to tools, APIs, and it can spawn other agents. And this is the way the document store is set up. So either internally or externally, you're going to want to have a document storage medium. And you have your full document, you have the text representation of that, and then you have the metadata, which is basically telling the LLM what's contained in that document. So it pulls the content from that. The query text is sent when someone makes a request. The query text is sent over. Basically, the way the content gets inserted into the vector store is text that's related to the document. The query text, you get a vector embedding that is a representation of that query text. And it matches, so it gets the vector information on this query text, so it's a vector representation of that text. Then that vector, along with the text, is stored in the database, and the context is returned when you're retrieving the information. I hope I'm making sense. So basically, you have a vector representation of the text, and that's how you use those vectors to retrieve the matches to these documents. So really everything is just a vector. When it's looking something up in the database, it's a vector representation, and it's a multi-dimensional vector representation. So typically two-dimensional, you have two points with a vector in between, and that's the relationship between two pieces of data. But this actually does it in multi-dimensions, and you can't even wrap your brain around that. But it's how various pieces of text are clustered together in terms of how they're related. So that vector representation is how close they're matched, and that it's that vector representation that is used to retrieve matching data to the query. Does that make sense? This is supposed to be basic.
Yeah, it's kind of a nearest neighbor. I think last years, Segovia was talking about a nearest neighbor. So it's right. Yeah, vector database. I don't know. Maybe some, have a more view about vector database, and it's kind of a nearest neighbor to look for. That's how the ChatGPT or LLM, try to work together to gather the data out of the whole entire corpus. So anyway.
Yeah.
If
So
you
I have
understand database, infrastructure and database structure, then sure, it makes great sense. And I'm not saying I do or I don't, but I'm saying in general, if you've never dealt with databases before, a lot of this won't make sense.
So the way we set up a vector storage database, a vector database storage, is you have your document store with your documents in there, the text representation of those, the metadata that says what's in that.
Mm-hmm.
Let me try to make this easier to see. Whoops.
For us old guys, thanks, man.
So you want to clean the source documents of any garbage, bad characters, that kind of thing. Get rid of anything that's irrelevant. And you take that source document, you're going to want to get the text of that source document, and you're going to cut that up into pieces. And it's the pieces that you're going to insert into the vector database. And you're going to do that with overlap, so that the LLM can see a match between the pieces. So let's say you have a couple of sentences that overlap, in those pieces, then the LLM can put those pieces together when it pulls everything out. You want to generate vector embeddings that represent the text in those pieces, and you get back an embedding, which is the vector representation of that text. And then you're going to take that and insert it into the vector database. And in there, you've got the vector index, which is the vector representation of that text. You have the text and the associated metadata. And that's what you're going to put in the vector database. So in here, I have a vector index. And when I get a query from the user, I'm going to generate an embedding for that query. And I'm going to query the vector database using those vectors. I'm going to come up with a matching set that closely matches the ones that closely match those vectors from the query, and that's what I get back from the vector database. So that's basically how how you create the storage is you're gonna end up with a vector database that has a vector index, the text, and the metadata, and then those are all going to map back to your document store. Typically, there's a separate table in the vector database that has an index that's related to this vector store so that it can find the source document that's related to what it's pulling out of here. So it can go back and give you a citation for what's in the document store. Yeah, and then you're going to update the document store as well with an index related to the vector database. So you have a way to refer to both. And then the retrieval, I just kind of went over that, but here's how the retrieval works. The user has a prompt, the vector embeddings are generated related to that prompt, and then you're formulating the query with the vector representation of that query, and you're getting index IDs and retrieving the context from the vector database. Then you're injecting the context into the prompt and querying the LLM. So there's two calls. You're doing your vector call, getting the related context, and you're injecting that into the prompt before you query the LLM. So the LLM has all of the